Ever felt like you're just, drowning in information? You've got these stacks of articles, research papers, notes. There's gold in there, but it's buried deep. That's really the challenge we tackle every time here on the Deep Dive. We try to cut through all that noise and get straight to the core insights. Today, we're embarking on a pretty deep dive into entropy. Now, that's a concept that sounds complex, maybe a bit intimidating.
It often does, yeah.
But it's absolutely fundamental. I mean, really key to understanding energy efficiency, even things like the direction of time in our universe. So our mission today is to go beyond just the textbook definitions. We want to understand not just what entropy is, but, why it behaves the way it does and what its, frankly, profound implications are. We're drawing our insights from a really comprehensive thermodynamics textbook this time. So we're getting into the weeds a bit. But the goal is to extract that core wisdom, not just recite equations.
Absolutely. To make it intuitive.
Exactly. So let's get into it. Okay, let's unpack this. When we talk about energy, the first thing that usually comes to mind is the first law of thermodynamics, right? Energy is conserved. Simple enough, conceptually.
Right. Can't create it or destroy it, just change its form.
But then the second law throws this curveball called entropy. And like you said, it doesn't play by the same rules. It's not conserved. So what's the best way for us, and for you listening, to shift our thinking and really grasp what entropy is all about?
Yeah, you've really hit on the core challenge there. Unlike energy, which, you can always account for, it just changes form, entropy is fundamentally different. It's maybe best thought of as a measure of the quality of energy, or perhaps more accurately, the amount of, disorder or randomness in a system.
Disorder, okay.
The key insight, really, is that while the amount of energy is conserved, its usability, its quality, let's say, can degrade. And that degradation, that loss of quality, is directly tied to an increase in entropy.
Ah, okay. So it's linked to how useful the energy is.
Exactly. And the whole idea, the concept of entropy itself, it actually stems from observing how real-world processes work, or rather, how they don't work perfectly. Think about R.J.E. Clausius back in the mid-19th century. He was wrestling with heat engines, trying to figure out why you just couldn't get 100% efficiency.
Right, the limits.
Exactly. And his breakthrough work led him to this mathematical relationship, the Clausius inequality. Basically, for any cycle, if you sum up the little bits of heat transferred divided by the temperature at which they're transferred, that sum is always less than or equal to 0.
Okay.
And that inequality was the key. It showed him there must be some property, like volume or temperature, are properties whose change only depends on the start and end points, not how you got there.
A state property.
Precisely. And he named this new property entropy, symbol S. So, unlike energy, entropy can be generated. It can be created out of nowhere, essentially, for any process that isn't perfectly, ideally reversible, which is, let's be honest, pretty much every real-world process.
Yeah, everything real.
Entropy is created. We often call this entropy generation, or SLIGen. It's a direct measure of how irreversible, how inefficient that process is. The more irreversible it is, the more entropy gets generated.
Wow, okay. That's a powerful idea. So if it's always being generated in real processes, what does that tell us about, larger systems? Or even the universe itself?
Well, that leads us straight into what's often called the increase of entropy principle. It's fundamental for any isolated system, and that just means a system that doesn't exchange any energy or mass with its surroundings. Its total entropy can only ever increase. Or, in the absolute best case, perfectly ideal reversible scenario, it might stay constant.
But it never goes down.
It can never decrease. Never.
Yep.
Now, this is a really crucial distinction for you, the listener, to internalize. While the entropy of a specific thing, a specific system, can definitely decrease.
Like my coffee cooling down.
Exactly. Perfect example. The coffee loses heat, its molecules slow down, become slightly more ordered, its entropy drops. But
there's a but.
There's always a but with the second law. The total entropy, meaning the coffee, plus the air it's releasing heat into, the surroundings, that total entropy, when you consider them together as an isolated system, always increases during that real cooling process.
So the increase in the air's entropy is bigger than the decrease in the coffee's entropy.
Precisely. The universe, or at least the relevant part of it, gets messier overall, even though the coffee itself got tidier. And if we really zoom out, way out, the universe itself can essentially be considered an isolated system.
Right.
Which means the total entropy of the entire universe is continuously increasing. It's always moving towards a state of greater disorder, more randomness, less available energy for useful work.
Kind of mind-bending.
It is, and it's why this isn't just some obscure engineering concept. It fascinates philosophers, economists, environmental scientists, because it seems to point to a fundamental directionality of time and processes, a sort of cosmic decay, if you will.
Wow. Okay, so you mentioned irreversibility creating entropy.
Yeah.
Can we make that more concrete? Like, how does the amount of irreversibility affect the entropy generated?
Good question. Let's take a simple heat transfer example. Imagine you have a really hot source, say at 800 Kelvin, and you need to transfer 2,000 kilojoules of heat away from it.
Okay.
Now, option A, you transfer that heat to a sink that's at 500 Kelvin. There's a big temperature difference there, 300 Kelvin. That transfer process will generate a certain amount of entropy because of that irreversibility, that temperature gap.
Makes sense.
Option B, you transfer the same 2,000 kilojoules from the 800 Kelvin source, but this time to a sink that's much closer in temperature, say 750 Kelvin. Only a 50 Kelvin difference now.
Right. Much smaller gap.
And what you find is that the amount of entropy generated in option B is significantly less than in option A. The smaller the temperature difference driving the heat transfer, the less irreversible it is, and the less disorder or entropy is created in the process.
So transferring heat across smaller temperature differences is somehow better, more efficient in an entropy sense.
Exactly. It minimizes the entropy generation, which is often desirable. It preserves the quality of the energy better.
That makes perfect sense for heat flow.
Yeah.
But what about, well, understanding entropy changes in the actual stuff we encounter, like air, water, refrigerants? How do we actually calculate these changes without getting totally lost?
Right, the practical side. Well, for many common pure substances like water or the refrigerants used in your fridge, engineers rely heavily on tabulated data.
Like steam tables.
Precisely. Steam tables, refrigerant tables. These list entropy values along with other properties like temperature, pressure, enthalpy at many different states. They establish a common baseline like setting the entropy of liquid water to 0 at the triple point, allowing us to accurately calculate the change in entropy between two states for, say, water flowing through a turbine.
Got it. So tables for pure substances. What about things like liquids and solids?
For most liquids and solids, we often make a simplifying assumption. They're incompressible. Their volume doesn't change much with pressure, and that makes the math much easier. Their entropy change depends almost entirely on temperature change. You can calculate it using the substance's specific heat capacity. And interestingly, for these incompressible substances, if a process happens at constant entropy, it also has to happen at constant temperature.
Oh, interesting. So constant entropy means constant temperature for them.
Under that incompressible assumption, yes. It's a neat shortcut.
And what about ideal gases? Air, for example, so common in engines.
Ideal gases. We have a couple of main ways to handle those. If the temperature changes involved aren't too huge, we can often use an approximate method with average specific heat values. It gives pretty good results quickly.
A simpler way.
Right. But if you have really large temperature changes, like in a jet engine combustor, the specific heats of the gas actually change quite a bit with temperature.
So the approximation breaks down.
It becomes less accurate, yes. So for higher accuracy in those cases, we use a more exact method that involves special tabulated functions, often denoted as 0, which account for that variation of specific heat with temperature.
So two tools. A quick approximation and a more precise method using tables.
Exactly. You pick the one that suits the problem and the required accuracy. For small temperature differences, they give almost identical answers. For big ones, the exact method is definitely preferred. And building on that idea of calculating changes, there's a really crucial concept called the isentropic process.
Isentropic, meaning constant entropy.
Yes, iso meaning same, tropic related to entropy. So constant entropy. It's an idealized process.
Okay, why is an ideal process useful?
Because it represents the absolute best case scenario, the theoretical limit of performance for many devices. An isentropic process is one that is both perfectly reversible internally and also adiabatic, meaning no heat transfer occurs.
Reversible and no heat transfer, got it.
So think about devices like turbines, compressors, pumps, nozzles. Their job is to change the energy state of a fluid. The isentropic process tells us the maximum possible work output for a turbine, or the minimum required work input for a compressor, if everything worked perfectly, with no friction, no heat losses, no irreversibilities whatsoever.
So it's the benchmark, the gold standard you compare real devices against.
Precisely. We define efficiencies like turbine isentropic efficiency or compressor isentropic efficiency by comparing the actual performance to the ideal isentropic performance. It tells engineers how much room for improvement there is.
That makes a lot of sense. So it's the theoretical best. Now, if we want to actually see these processes, visualize them, numbers are great, but sometimes a picture helps. What tools do we use?
Absolutely. Visualization is key. And the most fundamental diagram for entropy is the temperature entropy diagram, or TS diagram.
Yours with S.
On this diagram, temperature is on the vertical axis, entropy on the horizontal. What's really neat is that in isentropic process, constant entropy just shows up as a straight vertical line. Easy to spot.
Simple enough.
And here's a really powerful insight. The area under the process curve on a TS diagram represents the heat transferred during that process, but only if the process is internally reversible.
Okay, area equals heat, but only for the ideal reversible case.
Correct. It gives engineers a visual way to assess heat interactions, especially in theoretical cycles.
Are there other useful diagrams involving entropy?
Oh, yes. Another incredibly useful one, especially for engineers working with things like steam power plants or refrigeration cycles, is the enthalpy entropy diagram. The aged S diagram, often called a Mollier diagram.
Enthalpy entropy.
Okay.
Here, enthalpy, which is related to energy content, is usually vertical and entropy is horizontal. The beauty of this diagram is that for steady flow devices like turbines and pumps, the vertical distance, the change in enthalpy, directly relates to the work done or received.
So vertical distance is work. Roughly speaking, yes. And the horizontal distance, the change in entropy, directly shows you the irreversibilities. A process moving to the right means entropy is increasing, meaning there are inefficiencies.
So you can see both work and losses on one chart.
Exactly. It's a very practical tool. And just to tie it back, think about that classic Carnot cycle, the most efficient heat engine cycle theoretically possible.
Right.
On a TS diagram, the Carnot cycle forms a perfect rectangle. You have two horizontal lines representing the constant temperature heat addition and rejection, isothermal processes, and two vertical lines representing the constant entropy compression and expansion, isentropic processes.
The rectangle. Neat.
And the really elegant part is that the area enclosed by that rectangle directly represents the network output of the cycle per unit mass. It visually shows you how work is derived from heat flowing between two temperatures in the most efficient way possible.
Okay, this is great. We've covered calculations, principles, benchmarks, even how to visualize it. But let's circle back to that fundamental question. What is entropy, really? We use the word disorder, but it still feels a bit abstract, like there's more hiding underneath. Can we unpack that deeper meaning?
You're absolutely right. The disorder analogy is useful. It gets us partway there, but it doesn't capture the full picture. At its absolute core, entropy is fundamentally about probability and information. It's a measure of the number of ways the microscopic components of a system, the atoms, the molecules, can be arranged while still looking the same from a macroscopic point of view.
The number of ways.
Okay. Think about it. In a solid, molecules are pretty much locked in place in a crystal lattice. There aren't many ways to rearrange them without fundamentally changing the solid. So low entropy.
Very ordered.
Very ordered. Now think about a gas. Molecules are whizzing around randomly, bouncing off each other. There are countless ways you could swap molecules around, change their speed slightly, and macroscopically, it would still just look like the same gas at the same temperature and pressure.
Many more possible arrangements.
Vastly more. And that means much higher entropy. More microscopic possibilities correspond to higher entropy. This connects directly to the work of Boltzmann and Gibbs, who formalized entropy in terms of statistics and probability. A system naturally tends to evolve towards states that are statistically more probable, which just happen to be the states with the most possible microscopic arrangements, the states of higher entropy.
So it's like nature prefers the states that have more ways of existing.
That's a great way to put it. It's statistical mechanics in action. This is why heat flows from hot to cold, why gases expand to fill a volume. These processes move the system towards states with vastly more microscopic possibilities, higher probability, higher entropy. And this ties into the third law of thermodynamics, too. It basically states that the entropy of a perfect crystal at absolute zero temperature, 0 Kelvin, is zero.
Zero entropy.
Zero. Because at absolute zero, theoretically, all molecular motion ceases. There's only one possible microscopic arrangement, the perfect motionless crystal lattice. That provides an absolute baseline, a reference point of perfect order.
Wow, okay. So low entropy is ordered, high entropy is disordered or has more possibilities. How does this connect back to the idea of energy quality you mentioned earlier?
Excellent question. It helps us distinguish between organized and disorganized energy. Think about energy in a rotating shaft or electrical energy in a wire. The motion or flow is directed, coherent. That's organized energy. It can easily be used to do useful work, lift a weight, power a motor.
Right, useful energy.
Now think about the internal energy of a gas. The random, chaotic, kinetic energy of all its molecules bouncing around, that's disorganized energy. We perceive it as heat or thermal energy. While that energy is certainly there, first law, it's much harder to extract useful work from it, especially if it's just sitting there at ambient temperature. Its randomness, its high entropy state, makes it less available.
So high entropy means low quality, less useful energy.
In a sense, yes. That's why we sometimes hear the phrase, work is entropy-free. When energy is transferred purely as work, like by a shaft, no entropy is transferred along with it. But when energy is transferred as heat, entropy is transferred. The first law says energy is conserved in quantity. The second law, through entropy, tells us about the conservation, or rather the degradation, of energy quality. Every real process increases total entropy, which corresponds to a decrease in the amount of energy available to do useful work. The energy is still there, just less organized, more dispersed, harder to harness.
That degradation aspect feels very relevant to everyday life, actually.
It absolutely is, more than people realize. Think about the effort it takes to keep your house tidy or your desk organized. The natural tendency, without energy input, is towards messiness, towards higher entropy.
My desk can confirm that.
Mine too. Or think about information. Once a rumor spreads, it's incredibly difficult to unspread it. The information disperses, mixes, that's an entropy-like process. There's even a library analogy. Imagine two libraries with the exact same collection of books. One is perfectly cataloged and shelved. The other has books just piled randomly. The first law might say they have the same energy, same books, but the second law, through entropy, tells us the ordered library is far more valuable and useful because of its low entropy state.
That's a great analogy.
People even apply it metaphorically, like friction in mechanics generates heat and entropy, degrading performance. Some say friction in the workplace, disagreements. Poor communication generates metaphorical entropy, hindering productivity.
Huh. I hadn't thought of it like that.
Or even unrestrained actions. An uncontrolled chemical explosion is highly irreversible, generates a lot of entropy, and causes damage. Some philosophers might even say, perhaps stretching it a bit, that unrestrained opening of the mouth to scatter angry words is an irreversible process generating emotional entropy and causing harm that's hard to undo.
Okay, that's taking it far. But I see the parallel, the irreversibility, the increase in disorder.
It speaks to this fundamental tendency. Sir Arthur Eddington, the famous astronomer, had a beautiful way of putting it. He compared entropy to things like beauty or melody. He said these are all features of arrangement. They only exist when you view the parts together in relation.
Features of arrangement.
But, he noted, entropy is unique because, unlike beauty, it can pass itself off among the aborigines of the physical world. It has a measure number. It's quantifiable. It tells us something fundamental and mathematical about the structure, the organization, or lack thereof within any system.
Wow. That's
Yeah.
a lot to think about. Well, we certainly set out today to try and demystify entropy, and I really hope that for you listening, you now have a much clearer picture of this really fundamental concept and its truly far-reaching implications.
It touches so much.
It really does. It's clearly not just about thermodynamics in some engine somewhere. It's about understanding the arrow of time, the direction of change, this inherent tendency towards, well, disorder in the universe around us. So maybe as you go about your day, just consider this. If the universe as whole is constantly moving towards a state of greater disorder, higher entropy, what does that really imply for all our long-term efforts to create and maintain order? Whether that's in our technology, in our societies, even just organizing our own lives. Does this underlying principle suggest some kind of ultimate fate for all organized systems? And if it does, how does that maybe shape our understanding of progress or failure, or even just the value of the act of creation itself against this constant tide? Something to ponder.